So here we go for the starters for chapter 7.3. Usual routine, when I get to the end of the question, you pause it, try it, and then I'll go through the answer. So given x is equal to t cubed over 3 minus t squared plus 7, find the acceleration when t is equal to 3. So we should remember that to get from position to velocity to acceleration, we differentiate with respect to t. If we were going in the other direction, we'd integrate with respect to t. So that's the key facts that we need. So now we're just going to differentiate. V is equal to dx dt. So we write down the constant, a third, bring down the power, subtract 1 from the power. Minus, right, so the constant is -1 in effect, bring down the power 2, subtract 1 from the power, t to the power 1, which we wouldn't bother to write usually, and 7, the gradient of 7 is 0, of x equals 7 is 0, so that vanishes when we differentiate. So we've now got t squared minus 2t. So to get to the acceleration, we differentiate the velocity, and we get 2t minus 2. So at t equals 3, a is equal to 2 lots of 3 minus 2, which is 4 meters per second squared, assuming that x was in meters and t was in seconds to start with. Okay, our second example, we're going to take a non-uniform rod which is attached, hinged at the point A to a horizontal plane. The length of that rod, let's call it 5 meters. And we're going to make that rod of mass 10 kilograms, but we don't know its centre of mass is, so we're going to have that distance to the centre of mass as x. We've also got a force acting at the other end of the rod. Call it 80 newtons at an angle of 60 degrees to the rod. And the question is, find x. Okay, now we could resolve horizontally and vertically and that kind of thing, but the key thing here is that we want the distance. We want the distance from a point to the centre of mass. So we've learnt with static questions that we take moments about the point where the most unknown forces act as one of the things that we do, unless we want the distance from a point, in which case we take the moments about that point. So first of all here, let's just recognise that we've got two other forces on this diagram. We would have a vertical component and a horizontal component acting at the hinge. We could call those capital X and capital Y. But because we want the distance from A, when we take moments about A, the component moment due to X and the moment due to Y will vanish. Yeah, they will have no effect. So we're going to take moments about A. The anti-clockwise will equal the clockwise. The component due to X will be 0. The component due to Y will be 0. In the anti-clockwise direction, then the only force that is having effect in the anti-clockwise direction, a turning effect, is the 80 Newton force. So we need the perpendicular distance to its line of action. So its line of action is up here. Its perpendicular distance then is this one here. And then this is opposite the angle 60. Yeah, it's opposite the angle 60. So this will be 5 sine of 60. So the moment due to the 80 newtons is going to be 80 times 5 sine of 60. Okay, now we've got to look at the forces which are having an effect in the clockwise direction. So that's this one here, the 10G. The distance to its line of action is going to be here. And this angle, oh, I forgot to define in the question. So let's say this angle here is 30 degrees. Okay, so let's go back then. So this will be x cos of 30 degrees. So we're going to get x cos of 30 times 10g. So x equals 400 sine of 60 over 10g cos of 30. Now hopefully you recognise that sine 60 and cos 30 are both root 3 over 2. So those will cancel. So here we get 40 over g, which is roughly 4 metres. You can tap it in the calculator and check. 4.1 metres, I think it comes out to be. Okay, sorry if you I didn't get the 30 degrees in there to start with, and I'll see if I can find a way of putting that in. 3. So this is the thing we've been working on recently. That's 15 metres per second. That's an angle of 40. And we want its position. Find the position when travelling perpendicular to direction of projection. So it's going to do this. Somewhere here we've got the particle, the point angle of projection. This speed was 15 at 40. It's got a new speed v, and this angle, to make that a right angle, to make it perpendicular, will be 50 degrees. Okay, so we know then the key into these questions is that the horizontal speed is constant. So constant acceleration horizontally, and now we want the components of these two. So we've got this one here, which will be v cos of 50, and this one here will be 15 cos of 40. Yeah, it's the same because there's no acceleration in that direction. So we know that 15 cos of 40 equals v cos of 50. So v equals 15 cos of 40 over cos of 50. Okay, so we've got v, we can tap that in the calculator, and that comes out to be about 17.9 metres per second. Okay, now we're still looking for the position, but to get the position we're going to need to know the time at that location first of all. So we're now thinking about the time when it's perpendicular. So to do that we're going to use constant acceleration vertically. Let's just define that as the origin, which we forgot to do earlier. So constant acceleration vertically, and we've got vertically u is equal to 15, and this is opposite, so it's going to be 15 sine of 40. So 15 sine of 40. A is going to be negative g because we've taken positive up. V is (17.9) sine of 50. So that's coming from here on the diagram. So the vertical speed here is v sine of 50. But what do we notice there? It's going downwards. So that must be negative. And that's probably the most likely mistake that people make on there. That's negative because this speed now is down. And we've got positive as up. T is the time that we're looking for. So what equation are we going to use? V equals u plus AT. Substitute in 15 sine of 40 minus GT is equal to minus 17.9 sine of 50. So T equals, adding the GT across, we get 15 sine of 40. Add the 17.9 sine 50 back, 17.9 sine of 50, all divided by G. Tap it in the calculator, and that should come out to be about 2.4, 2.38 seconds. Just check that you've got that. Okay, so we're now trying to find the coordinate. And that's the coordinate relative, the position relative to O. So we're now going to have to think about, first of all, the horizontal motion. Well, its position is equal to its horizontal speed times the time. So its horizontal speed is from here. We've already got the horizontal speed, haven't we? The horizontal speed is here, isn't it? 15 cos 40. So it's 2.38, that's the value of t, times 15 cos of 40, because that's remained unchanged. So that comes out to be 42. That doesn't look right to me. That's going to be 30 cos of 40. It's going to be about 30. You'll need to check that on a calculator. Yeah, so just check that, but it's about 30 meters. Okay, now consider the vertical motion and its constant acceleration again. And we get u equals 15 sine of 40. A is equal to negative g. T is our time, and we're looking for the vertical position. We probably should have used SX for that, the horizontal one. So S equals ut plus a half AT squared. Plus S0, but we're starting at the origin, so we don't really need that. So we've now got 15 sine of 40 times the time, which is 2.38 from above, plus a half negative g, and then the t squared, which is 2.38 squared. Tap it in the calculator, and that's minus 4.81 meters. Okay, so we've now got the horizontal position here and the vertical position here, and the 30 just needs checking on a calculator. Hope that's clear and been a useful little bit of practice on those things.